Hey everyone, it's Presley at ActOutGames.com here, and today there's a lot of really new things happening that I want to talk to you about. First of all, we got a grant from Google's Making in Science team, which is helping us make a lot of new educational content, just like this video here. It also helped us buy all the stuff for the new set, as well as some new equipment, so we can make some high quality stuff that I hope you guys really like. Thanks so much to the team at Google Making in Science for giving us this grant and really helping us out. Second, we're going to be migrating all of our EDU content onto a new channel for those of you who want to watch our EDU content but don't really want to keep up with the other things that we're doing. The new channel is called Bite-Sized EDU, and there'll be a link in the description if it sounds like something you would like to check out and hopefully follow. We'll be posting another version of this video over there, as well as there's going to be a lot more to come. Big things are happening here at ActOutGames, and a huge thank you to you guys for helping make it happen. We couldn't do it without all of you guys. I know it sounds cheesy, but that's the truth. Now let's talk about some laws of science. In this series, we're going to be taking a look at 10 fundamental laws of science that will help you better understand the world around you. A lot of these will seem pretty obvious to you when we first talk about them, but we're going to try and take a look back in history to see what people thought before these were accepted as scientific laws. We've picked these 10 laws to talk about in this series because we think that with a good understanding of them, you'll be able to look at the world around you in a new way and open your eyes to all of the objects and forces interacting around you all the time. In this video, we're going to be covering Newton's first law of motion, which I bet many of you have heard before. There's a few different ways this one is said, but the one we're going to be using is, an object at rest will stay at rest, and an object in motion will stay in motion, in a straight line, at a steady speed, unless acted upon by an unbalanced force. That sounds pretty complicated, and there's probably a few words we should define there, but let's start with what people thought about motion during Newton's time. Like all good science, it started with observations. What do people observe when they're investigating motion? A few thousand years ago, people investigated motion, and this is what they saw. I put a block on the table here, and it doesn't move unless some kind of force acts on it. A force is a push or a pull. It could be my hand pushing, or my hand pulling, or it could be even gravity or a magnet pulling. Any push or pull is a force. So we're looking around, and we see anything that's sitting still won't move unless something makes it move. That's the first part of Newton's first law. An object at rest will stay at rest unless an unbalanced force acts on it. What about things that are moving? I push the block, and when I stop pushing, it stops. I pull the block, and when I stop pulling, it stops. So from that I can infer that an object needs a force to keep it in motion, or else it will stop. If that were true, then the second part of Newton's first law would be, an object in motion will stay in motion only while being acted on by an unbalanced force. Otherwise, it will come to rest. For many thousands of years, this is how people understood motion, but it turns out they were wrong. Before Newton wrote his first law, Galileo did some experiments something like this. So I have this metal washer here, and I also have a few different surfaces. Let's go ahead and do our experiment. So first, I put the washer on the sandpaper, and I flick it, and it doesn't go very far. Then, I put it on this felt, and I flick it, it goes a little bit farther. Then, I put it on the table here, and I flick it, and it goes even farther. Then, I put it on the glass here, and I flick it, and it goes almost to the end of the glass. Why is this happening? Why is it going further on the glass than it does on the sandpaper if it's just returning to a natural state of being stopped? We now know the answer is friction. There are tiny little rough spots on all of these surfaces, and when these surfaces rub against each other, the tiny little rough spots push against each other. They push against each other. That's a force. Suddenly, we can see that a force is acting to stop the motion, and it's not just stopping on its own. Galileo and later Newton theorized that if as friction got lower and lower, the object would go further and further without a force acting on it, then maybe if there was no friction, it would move forever. That turns out to be true, as we'd see later when we finally made it to outer space and could experiment in a place with no friction. If an astronaut in space threw a ball, that ball would keep moving forever unless it ran into something or got close enough for gravity to pull it in. I wonder if anyone's ever done that in space. That would actually be pretty cool. Maybe there's something out there right now that's hurtling through space that someone threw in a spacewalk like 20 years ago. Anyway, that explains the gist of Newton's first law. An object at rest will stay at rest, and an object in motion will stay in motion, in a straight line at a steady speed, unless acted upon by an unbalanced force. We still need to talk a little bit about what it means to say an unbalanced force, but we're going to save that for another video. For now, just look around you and know that anything that's speeding up, slowing down, or turning is being acted on by a force. See if you can identify what force is doing that work, and tell me what you see in the comments below. Hope this all makes sense, and you have a good understanding of Newton's first law now. We're going to be doing more detail in the next episode, so please subscribe and follow along to learn more about the 10 laws of science that we picked. Thanks again to the Google Making in Science team for giving us this grant, and thank you for watching. Go check out Bite-Sized EDU and tell us what you want to learn about with us. Thanks for watching, and I'll see you tomorrow.